Here we are, chapter 3, water. So this chapter, I think, really is trying to get you excited about water and also to reinforce this idea that water is what makes life on Earth possible, right? So even if you look at space exploration, right, we're sending rovers to Mars, we're looking for signs of life, we're looking for signs of water. So there's a ton of really neat properties that water has, and we're really going to focus in and look at those properties that help water support life on Earth. So fun fact, right? Water is the only common substance that exists in both a solid, liquid, and gaseous form. But what we'll find is that water has these unique emergent properties that help make the Earth suitable for life. So remember, emergent properties means something that arises at a particular level of organization, right? So hydrogen and oxygen doesn't do this, but when they're combined in a specific H2O, right, we get these properties that make life possible. And a lot of this has to do with the structure of a water molecule. So this is where all that bonding and the interaction between electrons comes in from the previous chapter, right? So here we see that water is a polar covalent molecule, right? Oxygen is larger, it's more electronegative, and so when it's sharing electrons with hydrogen, that's our covalent bond, it's a polar covalent bond. And so we're seeing a partial positive by the hydrogen and the partial negative because the electrons are spending more time down by the oxygen. Get my laser pointer out. There's our partial negative. What this then sets up is an attraction between the partial negative oxygen and the partial positive on that adjacent hydrogen. And that's where we saw the hydrogen bond, right? We talked about hydrogen bonds already. And so what we're going to see is this is responsible for so many of these important properties of water. So we're going to focus in on 4 here. The fact that water acts cohesively. It plays a huge role in moderating temperatures. We'll think about how that affects both ecosystems and organisms. Water expands upon freezing, which just sounds like random trivia, except if you think about the fact that ice floats, life can exist underneath it, right? If ice always sank, lakes would just fill up with ice. Okay, and we'll also look at its role as a solvent. Okay, so cohesion. What we're looking at here is you have basically a series of water molecules that are holding on to each other. That's what cohesion refers to, right? Hydrogen bonds holding water molecules together. Adhesion is the attraction to a different substance, right? So we see the water molecule sticking to a cell wall in a plant here. And so this is a property, this is the perfect example. You could do this, right? If we were in class, I'd dip a paper towel in water and you'd see the water kind of wick its way up the paper towel. That shows you cohesion and adhesion. Well, if you think about this on an ecosystem level, which is much more important than a paper towel, plants are gathering the water in their root system, but you need that water to go all the way up to the very top, right? To the leaves in this case. And so what we're going to see happening, they're zooming in on the structure, the trunk of the tree, all of these parts of a tree, the roots, the leaves, all have these cells that act as these hollow tubes. And so water is able to move up those. And then it gets even more complicated when evaporation happens from the surface of the plant. As those water molecules break free, right, they were pulling other water molecules up behind them. And so you just have this whole chain of water molecules getting pulled up a plant. In fact, that's the only reason trees can be this tall, okay? Water can't actually move that high on its own, but it's that evaporation from the surface. That's often referred to as transpiration or evapotranspiration from the surface, from plants. And then, so if you think about a rainforest, right, part of the reason there's so much moisture and therefore so much rainfall in a rainforest is all that evaporation happening from plants. You cut the trees down, you no longer get the rain. Okay, tangent. All right, so that was just the close-up of what those water conducting cells look like. So that's cohesion and adhesion. Another thing that allows is organisms, right? Like this spider is hanging out on the surface of the water. And so water has what we would call surface tension. And basically, it's still these hydrogen bonds between adjacent water molecules, right? That make it, you'd actually have to break that hydrogen bond to break the surface tension. And this water actually has an unusually high surface tension. And so that allows some organisms to walk around on the surface, right? But that again is basically still cohesion. Okay, another huge role that water plays is this ability to moderate temperature. So here in Colorado, we don't experience this as much, but if we were in class, I'd say who's ever, lived in Southern California, been to Southern California. In coastal environments, you see this really dramatically. So let's just look at LA for an example, right? So right here on the ocean, the airport, at least at LA, sitting at like 75 degrees. That's a beautiful day, right? You move inland, and they've got a little scale here, 40 miles. Move inland, right, to Riverside, 40 miles, it's 96 degrees. Why? Why? The water, the ocean, is actually absorbing a ton of that energy, a ton of that heat, right? And so the areas along the coast are going to be cooler. So water absorbs heat from warmer air and releases stored heat to cool air. So it's always moderating. On a really cold day, LA is still going to be 75, right? Riverside might be 50, right, on a cold day in California. I think it gets that cold in California. Okay. So water absorbs and releases a large amount of heat with only a slight change in its own temperature. So the weird part about this is you have to think about temperature maybe a little differently than you have before. So temperature is actually a measurement of kinetic energy. And kinetic energy is just energy of motion. And so actually when you stick a thermometer, say in your mouth, and you look to see where the mercury goes, the mercury rises if the heat from your body starts making those molecules move more quickly, they actually have to spread out, and that's going to make that mercury expand, right? So temperature is really just a clever measurement of the amount of kinetic energy in something. So basically, with just a slight change in its own temperature, water can change the amount of kinetic energy a lot. We usually measure this by calories. The book went into a lot of detail about this, right? And maybe you actually remember this from a previous class. A calorie is the amount of heat required to raise the temperature of 1 gram of water, just a little bit of water, 1 gram of water by 1 degree Celsius. Right? That's the definition of a calorie. When we talk about calories as far as food is concerned, we're actually on food packaging, it's actually kilocalories, 1,000 calories that we're talking about. Okay, so a lot of times when we talk about water then, we refer to this phenomenon, the amount of heat that it can absorb or lose, as specific heat. Okay, specific heat is the amount of heat that must be absorbed or lost for 1 gram to change its temperature by 1 degree, right? So we go back to that calorie idea. And this is all based off of water. The specific heat of water is 1 calorie per gram gives you a degree of Celsius change. Anyway, the big picture, if you're going like, what is she talking about? The big picture is water resists changing its temperature because it has this property that's high specific heat. Okay, so this is important, say, in ecosystems. We can imagine that the plant life is going to differ dramatically between LA and Riverside, but it's also really important inside the human body, right? You're made up of something like 70% water, and part of that role of water is to resist major changes in temperature, right? You want your body temperature to stay at 98.6, and water helps you do that. Water also helps you do that through things like evaporative cooling. So if you start getting to the point where your body temperature is actually going to rise, which a lot of your proteins won't like, you start to sweat, okay? The whole point of sweating is to get this evaporation. So evaporation is when you turn a liquid into a gas, right? You vaporize it. And that is going to take energy with it. So with water, we talk about the heat of vaporization, and this is the amount of heat that a liquid has to absorb before 1 gram of it is converted into a gas. And so that sweat on your face, as it turns into a gas, it's taking that energy, it's taking that heat with you. And so we get this evaporative cooling. Now, humans, of course, sweat. You'll see dogs panting. They're trying to do that evaporative cooling off of their tongue. Okay, so the ability of water to resist that change in temperature is huge for life. Okay, one of our other factors here was this idea that ice floats. And I know this sounds really strange, that this is a major property that allows life to exist, but it's true. So notice what's happening here. So in a liquid, right, think about, there, I just had my water bottle, right? So to swish some liquid around, the molecules have to be able to move freely. And so what you'll see happening in a liquid is that those hydrogen bonds are breaking and reforming, and so they can keep kind of adjusting to the shape and size of their container. When water loses enough energy, we're going to turn into a solid. And what happens in that moment of freezing, right, is basically we develop this kind of this repeating pattern where the hydrogen bonds are fixed in place and the water molecules are held in this very precise pattern. The key thing here to notice how much more space is in the middle of these 6 atoms as you might find in the middle of these 6 atoms, right? So water, right, actually expands when it forms ice. And so you have the same amount of matter, the same number of molecules in more space, which means it's less dense, right? Things float when they're less dense. A piece of wood floats because it's less dense. Ice floats because it's less dense than water, right? So it has that orderly shape that makes it less dense. In fact, water is most dense. Here's, for your Tuesday night trivia or whatever, it's most dense at 4 degrees Celsius, right? It freezes at 0 degrees Celsius, but it's most dense at 4 degrees Celsius. So maybe you've felt this if you've been in like a high mountain lake late in the summer, the surface has started heating up, and the coldest water will actually be at the bottom. Okay. And then another property super important about water, some people refer to water as the universal solvent, and that's not entirely true, but water is really good at dissolving a lot of things. And so here we're looking at how water is actually dissolving table salt. And so a couple just terminology things. So once we'd had that salt water mixed up, we'd say it's a solution, right? It's a liquid that's completely well mixed substances, right? The solvent is the dissolving agent. In this case, that would be water. And the solute is the substance being dissolved. That would be the salt in this case. Okay. So water can't dissolve everything, but water is really good at dissolving things that are polar. Okay, it's not very good at dissolving non-polar things because actually, let me just go back. Notice how water is dissolving this salt. All of the negative oxygens end up kind of cuddling up with this positive sodium, and all of the positive hydrogens are kind of cuddling up with this negative chloride, right? And so the polarity of water is what allows it to pull other charged or polar molecules apart. They call that a hydration sphere when water kind of encircles these different substances. So this particular protein is water soluble because notice when we zoom in here, on the outside of the protein, you can tell there's these polar portions, right? And so water can have that same activity. Water can dissolve some other compounds as well. But how do I say this? That's a bad way to say it. Okay. Let's talk hydrophobic, hydrophilic. So because these are terms that'll come up a lot. Hydrophilic substances are attracted to water or have some kind of affinity for each other. Hydrophobic substances, right? Literally, the word means like water fearing. It's not really scared, but they don't have an attraction to each other. So things like oils are hydrophobic. And right, just think about salad dressing. Water and oil don't mix. Water's not going to be able to dissolve the oil because there's no polar portion of that, and they're just going to try to stay away from each other. And so when we get into talking about cells and cell membranes, we'll see that a big portion of those cell membranes are actually made out of lipids so that we can kind of keep water either inside of the cell or outside of the cell. We'll get there. That's a few weeks down the road. Okay. So then we're going to shift gears and we're going to talk about pH. And we talk about pH here because we're thinking about how things have dissolved or dissociated in water. And really, when it comes down to it, when we talk about pH, we're talking about actually how water and other substances can fall apart. Let's look at water first. So in this equation, what we see, right, we have two water molecules, two H2Os. But spontaneously, right, this just kind of randomly happens as water molecules are bumping into each other. Sometimes a hydrogen from one will actually shift onto another water molecule. So now we have hydronium, right, which you see as H3O+. But a lot of times, honestly, we'll just refer to it as H+. And then we have hydroxide, or OH. Okay. How do I say this? In pure water, when we say its pH is 7, right, it's because we actually have, ready for this, 1 times 10 to the negative 7th hydronium ions. We'll come back to that thought, okay? When we look at pH, we're talking about the power of hydrogen, the concentration of hydrogen in a solution. Okay, in fact, maybe let's go there. Let's see if I can just write this out. It's going to be terrible handwriting. Okay, so when we're talking about pH, it's actually the negative log. I should just put this on the slide ahead of time, huh? Of the concentration of those hydrogens or hydroniums, right? Okay, this looks super complicated, but let's just break this down. So the little box just means concentration of. So we're interested in the concentration of hydrogen, okay? Now negative and log. The negative is going to tell you that you're dealing with an inverse relationship, okay? Lower pH numbers have more hydrogen, okay? That's the negative, it's inverse. Higher pH numbers have less hydrogen. And then log tells you that we're dealing with a logarithmic scale. Now, if you've taken lots of math, you know it's a scale 10, but this is basically like the Richter scale, right? It is a base 10, and what that means is if you go from a neutral pH 7, right, and you drop to a pH of 6, it doesn't sound like much, right? I've just dropped 1 on the pH scale, but you actually have 10 times more hydrogen ions. And when you hit 5, it actually becomes cumulative. You have 100 times more hydrogen ions. Okay, in living organisms, you pretty much have to stay between 6 and 8. And I will tell you in humans, so blood pH is at 7.4, and actually what's considered a normal range is 7.35 to 7.45. Like it's that tightly controlled inside of your body because swings outside of that are really damaging to proteins, right? So in fact, in humans, if you get as low as 6.9, that can be lethal, right? And so this pH scale, that logarithmic portion of this pH scale is actually really important. And so if we look at that, there they have pure water at 7, they put human blood there, etc. Some things inside of the human body are extremely acidic, right? So gastric juices inside of your stomach, all the way down, I kind of hate this scale because it's down to a pH of 2, super acidic. There's very little in the human body that I can think of that would be above this 8, where they're pointing out fluids of the small intestine. Okay, so it's pretty narrowly controlled. Okay, so real quick, something that is an acid is willing to donate hydrogens into a solution. Something that we refer to as a base is willing to accept those hydrogens. Now, where this gets a little confusing is as we talk about over here, they're mentioning different types of solutions, right? A basic solution has very few hydrogens. An acidic solution has lots of hydrogens. But if I were to say battery acid, what makes it an acid is its willingness to donate hydrogens into that solution, right? So that would make something acidic, right? Or bleach is an extremely strong base, right? It's willing to take hydrogens out of solution, and then when you have very few hydrogens left, it's a basic solution. Okay. Now, in order to keep life in such a narrow little window of pH, one of the things we use are called buffers. So a buffer just minimizes those changes. A lot of buffers are both weak acids and weak bases. In the body, the classic buffer is a protein. One end actually has an acid group, and if things start getting a little too basic, it can donate some hydrogen. The other end is actually an alkaline or a basic group, and it can actually accept hydrogens if things are getting a little too acidic in the body, a little too crazy. And so just like the term suggests, it buffers. It keeps you from having big swings, big changes. Another place then, if you want to think more ecosystem scale, sorry if I get a little I teach human anatomy, so I get into the human body, but if you think about a human scale, we're concerned about acidification of the oceans, right? In particular, the effects that might have on things like coral reefs. And so this is getting a lot of chemistry here for you. But basically what happens is CO2 from the atmosphere can dissolve into water, and it becomes a molecule called carbonic acid. And then carbonic acid can dissociate, it can fall apart, and this just happens spontaneously, into hydrogen, right, and a molecule called bicarbonate. But there's the hydrogen, right? So the CO2 in the atmosphere basically makes it so we end up with a lot of hydrogen, okay? That starts to make the ocean more acidic. The only buffer that we have, I shouldn't say the only, one of the buffers we have in the ocean is this molecule called carbonate, and that can help minimize the pH changes. But the big picture is that actually makes it, when you don't have carbonate to join with calcium, you can't build calcium carbonate, which is what the coral reefs are made out of. So big picture, CO2 in the atmosphere can actually lower the pH of the ocean. And in an attempt to prevent that acidification, one of the byproducts is the inability of some ocean organisms to actually build shells. We can talk about that more if anybody wants to get into this coral bleaching, because that's kind of interesting. But this is spelling it out here. Okay, so keep that in mind. Humans can have an effect, even on a global scale, as far as pH. Then we could get into acid rain, right? There's like lakes in New York State that have no fish because the water became too acidic, and on and on. I grew up in Ohio, and Ohio produces that acid rain. Okay, so taking it back to the very root here, right? When we look at those 4 properties of water, right? The cohesion and adhesion, its ability to absorb lots of heat, right? The fact that ice floats, and its ability to dissolve substances, it all comes back. I guess it's up here on the screen. It all comes back, which way? There it is. It all comes back to that polar covalent molecule that water is, and the hydrogen bonds that form between them. Okay. And then make sure, particularly if you're going on into some sort of health program, that you understand the pH scale, right? That for something to be acidic means it has a ton of hydrogen, right? And a low pH number. If something's basic, it has very little hydrogen. In fact, it will help accept hydrogen. Yep. If something is basic, it has very little hydrogen, right? And it's high on the pH scale. Okay, I hope that helps a little bit. We'll see what we do in class this week. Like normally I'd have you like weighing out things, and we're just gonna have to get creative. So anyway, I will see you guys in Zoom.